there, Math Hubbers. This is again your Math Hub buddy teacher, Marcus. In today's math video lesson, we'll be tackling about the symmetry isometries via hands-on explorations and transformation of the Euclidean plane using matrix representation. Before that, let us first define some keywords in our lesson and understand their relationship with each other as we move along in our lesson.
First word is congruence. What is congruence? So it is the term to describe two geometric figures that are identical in shape and size. Next is isometry. An isometry is a distance-preserving map from some space to another or to itself. Another one is symmetry. So, a symmetry is defined as a balanced and proportionate similarity that is found in two halves of an object. We also have transformation. So, transformation is a general term for four specific ways to manipulate the shape and or position of a point, a line, or geometric figure. Next is geometric transformation. When we say geometric transformation, it is any bijection of a set to itself or to another such set with some salient geometrical underpinning. Next one is rigid transformation. It's also called Euclidean transformation or Euclidean isometry. It is a geometric transformation of a Euclidean space that preserves the Euclidean distance between every pair of points. Euclidean plane is the plane that is object of study in Euclidean geometry. Lastly, we have matrix. You can say matrix or matrix. It is a set of numbers arranged in rows and columns so as to form a rectangular array. Now, because we study a lot of different types of geometric objects in geometry, we'll have correspondingly a variety of different criteria for what it means for those objects to be congruent. If you can remember in our previous lesson about Hilbert's axiom of congruence, we can easily distinguish two lines or two line segments or arrays or geometric figures or polygons to be congruent with each other when they possess the characteristics of having the identical size, measure, angles, and shape. So, by having these characteristics, we tend to think of them as being exactly the same as one another or congruent to one another because the length of the sides are same, the measures are the same, as well as the angles are the same and the shape are the same. And so, we don't care about anything else that might further distinguish them as long as they possess the mentioned characteristics. For example, if I have a whole collection of different angles, an angle being determined by where two line segments come together, then which of these sets of angles are congruent? How do we determine whether two angles are quite the same? Well, looking across this list of angles shown to you, I can find two of them as sketched are congruent and that they have the same angle measure. The measure in degrees are in radians, so if these two angles give us the same number, and so we'll say that those two angles are congruent. Now, when it comes with line segments, we consider two geometric figures as congruent with each other when they have the same length. So if we were to get a ruler and measure them, the two line segments must have one or must come up with the same number or measurement. And in these five given figures, we can say that it would be the first and third figures. Only these two have the same length, and if we were to get out a ruler and measure the length of these line segments, we would get the same number. So there's not much room for argument there, at least as far as Euclidean geometry goes. Moving on, with these sets of triangles, we can see that the third and fifth figure are congruent to each other. Now, in relation to this, under congruence, these two angles, these two line segments, and these two triangles, each of them are similar to their pair. But, although they are similar, they are also different. How? Well, if you can notice, each figure has a different position from their respective pairs. On the first one, the angles, notice that the second figure is a rotation of the first figure. On the line segments, the second figure is the reflection of the first figure, and on the triangles, the two figures are the reflection of each other. These changes in this position are what made them different, and this is called isometry. The word isometry comes from the Greek word iso, which means equal, the Greek word metron, which means a measure, meter. Now, an isometry is a mapping of metric space into another or on itself so that the distance between any 2 points in the original space is the same as the distance between their images in the second space. In other words, isometry is used to describe the process of moving a geometric object from one place to another without changing its size or shape. For example, imagine two ants sitting on a triangle while you move it from one location to another. The location of the ants will change relative to the plane because they are in the triangle and the triangle has moved, but the location of the ants relative to each other has not. So, whenever your transformation a geometric figure so that the relative distances between any 2 points has not changed, that transformation is called isometry. Although isometry has a lot to do with equal distance, it doesn't necessarily encompass the definition that all points under an isometry are going to move in equal distances as all others or all other points because, for example, in this illustration, we can see a rotation of a geometric figure as you notice. Point C has a lot shorter distance to move than point B does, mainly because C is closer to the center of rotation, so it's not that all points are moving in equal distance do we need here. So we want that isometry preserves distances. In the case of this illustration, however, far apart 2 points are before we apply an isometry, the images of those points will be the same distance away from one another after we apply the isometry. So isometry is transformation which preserve distances. Importantly, because it's a transformation, in particular, it's a function. Functions that for an input, it must provide us with a unique output for each input, and that shows us how those inputs are related to those outputs, or functions relating to domain, to a range. And transformation is the usual geometrical word that we give to functions which operate in some geometric space like the plane or Euclidean plane. And so, in the case of an isometry, we are talking about functions which take a point, any point in the plane r squared, and produce for us another point in the plane. So, we will often use the notation of prime. We are talking about isometry, and it's just another simpler way to understand what is t of a. For instance, we applied a transformation t to the point A, and the result is something we can call a prime. Just use prime in the notation to make things simpler. Now, in line with that, as we can recall in our linear algebra subject, we have been tackling or studying about transformation of vector spaces because the xy plane is really easy to use and put stuff in and is very easy to understand. Plus, it has non-trivial geometry associated with it. So, we have learned about linear transformation from R2 to R2, and isometry will be a subcategory of those. So, anytime we say the word isometry, we can think of it as a transformation from R2 to R2. But not every transformation qualifies as an isometry because we need it to preserve congruence. In other words, when we apply the certain transformations to a figure, what we need to get is another congruent copy of the same figure. So it has to preserve congruence. We can't destroy the congruence of a figure we apply an isometry. Because as per definition of a plane isometry, it is a function that is defined for any point of the plane, and informally, a Euclidean plane isometry is any way of transforming the plane without deforming it. For example, suppose that the Euclidean plane is represented by a sheet of transparent plastic sitting on a desk. Examples of isometries include: first, shifting the sheet 1 inch to the right. Next, rotating the sheet by 10 degrees around some marked point, which remains motionless. Third is turning the sheet over to look at it from behind. Notice that if a picture is drawn on one side of the sheet, then after turning the sheet over, we see the mirror image of the picture. Pretty simple so far, it's not that terribly complicated. Moving on, let's have these examples to further understand isometry. Suppose to say you and I are standing 6 feet apart and we apply an isometry to ourselves, and we end up somewhere else, but when we still have to be 6 feet apart. Even if there's a change in our orientation or in our location or a change in our reflection, our left hands becoming our right hands, but we still have the same distance apart in our images that we had in our pre-images, so that it is what is being conveyed right there. So, the distance between you and I in the pre-image has to be the same distance between you and the image. Another example, we let F a mapping of the plane into itself. Again, please remember that this time around we are not going from a plane to a line or plane to a cube or any like that. We are going straight on to the plane itself. Again, we shall be mainly concerned with the isometries of the plane. Going back, we say that F preserves distance, or F is a distance preserving. If and only if, or if, that's how you abbreviate that, if and only if, for every pair of points P and Q, the distance between P and Q is equal to the distance between F of P and F applied to Q, or simply we can use E prime and Q prime. Again, the distance between any 2 points P and Q has to be the same as the distance between their image points P prime and Q prime. Based on the illustration, we have 2 points P and Q, then we applied some transformation to them, and that's going to give us 2 image points P prime and Q prime. And F is an isometry exactly when those distances are the same for all points P and Q that we could have drawn. So the segment from P to Q and the segment from P prime to Q prime have to be congruent to one another. So what to not get confused about is that in the definition of isometry, it does not mean that every point will move the same amount of distance, but only the distance between 2 points remains constant, and so it doesn't necessarily mean that P is prime equal to Q prime. That would be the statement that all points are moving the same distance in their images as from their pre-image. So, going back, those 2 distances are equal if F preserves distance or F is distance preserving, where distance is a metric function on the space at hand, and in the context of plane transformation, DIST or dist is a common Euclidean metric. Take note that a transformation that preserves distance is also bound to preserve angles, and so we can say that F is an isometry when this is the case. We can also say that the measures of the distance of the points is the same under the mapping F. Now we have a brief understanding about isometry and its transformations. You might be tempted to think that in order to understand the effects of an isometry in a figure, you would need to know where every point and the figure is moved, but that would be too complicated. It turns out that you only need to know where a few points go in order to know where all of the points go. In line with this, let us have a brief recall about the transformation geometry or transformational geometry, or commonly called geometric transformation. In mathematics, transformation geometry is the name of a mathematical and pedagogic take on the study of geometry by focusing on groups of geometric transformations and properties that are invariant under them. When we say invariant, it means that the objects remain unchanged after operations or transformations of certain types are applied to the objects. For example, the area of a triangle is an invariant with respect to isometries of the Euclidean plane, which means that the area of the triangle remains the same even under any or multiple isometric transformation being applied to the object. When talking about geometric transformation, we have to be very careful about the object being transformed. We have two alternatives. Either the geometric objectives are transformed or the coordinate system is transformed. These two are very closely related, but the formula that carry out the job are different. We only cover transforming geometric objects here. Now, by a definition, a geometric transformation refers to a change that has occurred to a two-dimensional shape that has altered its position, orientation, or size. Now, as I have mentioned, we have to be very careful about the object being transformed because under geometric transformation, we have different classifications. Geometric transformations can be classified by the dimension of their operand sets, thus distinguishing between, say, planar transformations and spatial transformations. They can also be classified according to the properties they preserve. But we won't be going over each of them and just focus on isometries, which preserve angles and distances. In geometric transformation of isometries, we have three main classifications. These are: first, translation; number 2, rotation; and number 3, reflection. You may wonder, where is dilation? Isn't it also a geometric transformation? Well, a dilation is not an isometry since it either shrinks or enlarges a figure. With this, dilation amplifies or reduces distance between image points, which is contradictory to what isometry conserves or preserves, which is again the distance between points. Going back, the first classification is called translation. When you translate an object in the plane, you slide it around. A translation in the plane is an isometry that moves every point to the plane a fixed distance in a fixed direction. We can move the object by sliding it in a set number of units horizontally and vertically to a new position. Again, you don't flip it, turn it, twist it, or bop it. In fact, with translations, if you know where one point goes, you know where they all go. For example, we have this triangle ABC when translation is applied. The image is then moved or slides to the right. It can also be moved vertically or slide upward. We call the object in its new position the image, and as you have noticed, the object and its image looked exactly the same but are just in different positions. Both their angles, size, shape, and distance between 2 points stays the same or is preserved. The second classification is called rotation. What is rotation? So, it is when an object is turned around a fixed point by a set of number of degrees, either in a clockwise or counterclockwise direction. A rotation involves an isometry that keeps one point fixed and moves all other points a certain angle relative to the fixed point. In order to describe a rotation, you have to know the pivot point called the center of rotation. You also have to know the amount of rotation. This is specified by an angle and a direction. For example, you could rotate a figure about a point P by an angle of 63 degrees. But you need to know if the rotation is clockwise or counterclockwise. And based from our illustration, we have rotated it clockwise to a certain degree, which is at a 27 degree. Our image then will have 90 degrees angle. And you can see that the object and its image remain identical with each other. The distance between 2 points remain the same, as well as its size, and the object and its image are congruent to each other with the exception that the image has a new or different orientation from the object. Okay, lastly we have reflection. What is reflection? So, reflection transformation occurs when an object is flipped in a mirror line. This means that a reflection in the plane moves an object into a new position that is a mirror image of the original position. The mirror is a line called the axis of reflection. If you know the axis of reflection, you know everything there is to know about the isometry. For example, we have this triangle. Okay, so as you can notice, when an object undergoes reflection, transformation, it gives a new image which faces in the opposite direction. Notice that each vertex of the image is the same distance away from the mirror as the corresponding vertex in the object. At the same time, notice that both the object and the image are congruent to each other. Even the angles and the length of the sides remain unaffected. Now, in order to see if you truly understand the different classification, let's do a very short guess. Guess the classification the given object is transformed into. Okay, so number 1. We have this figure subjected to a transformation. What do you think is a transformation? Very good, it is a rotation. Next one, we have this figure subjected to a transformation. What do you think is this transformation? Awesome, it's a translation. For our third figure, we have this, and it is subjected for a transformation. What transformation is it? Next, very good, it is a reflection. For our fourth one, we have this figure. What do you think is the transformation it is subjected? Very good, it is a translation. Wow, you're getting the hang of this one. One last figure, and let's guess what transformation it is subjected to. This figure is transformed using what? Very good, it is a reflection. Good job, Madhavers! Now that we know what isometry and transformation is, as well as its classification, let us now have a brief summary of some relevant facts about isometries. As you can see in our table, we have 6 columns, and the first column is for our geometric transformation. The second column is to distinguish if the geometric transformation is a proper isometry or not. The third column is where the geometric transform is specified by. The fourth column is the number of invariant sets. The fifth column is the number of points or images parts, and the last column is the number of reflections. For our first geometric transformation, let's have reflection. Now, if you don't know it yet, isometries that preserve orientations are called proper isometries. A reflection in the plane moves an object into a new position that is a mirror image of the original position. Reflections are tricky because the frame of a reference changes. Left can become right and top can become bottom, depending on the axis of reflection. Thus, reflection is the rigid motion that does not preserve orientation. It preserves the distance as an example of opposite isometry. The orientation changes in a reflection. Clockwise becomes counterclockwise and vice versa. Because reflections change the orientation, they are called improper isometries. It is easy to become disoriented by a reflection, as anyone who has wandered through a house of mirrors can attest to. So, reflection is not a proper isometry, and it is specified by the axis of symmetry. It is because the axis of symmetry is a line that divides an object into 2 equal halves, thereby creating a mirror-like reflection of either side of the object. The word symmetry implies balance. Symmetry can be applied to various contexts and situations. Now, to recall, invariant is a term that refers to a property or a set that is preserved under the effect of a relation. The invariant sets of the reflection is shown in each point on the axis and each line, perpendicular to the axis. It is because when it comes to reflection, it preserves the distance of each point as well as its size and shape, and that both of the object and image perpendicularity of the lines to the axis are also preserved. With reflection, there's only one image and image parts reflected, and that is the pre-image or object being reflected. The next geometric transformation is translation. As what we have learned about translations, it preserves orientation. Left stays left, right stays right, top stays top, and bottom stays bottom. Isometries that preserve orientations are called proper isometries. Thus, translation is a proper isometry. Translation is specified by vectors of translations because vectors used in translations are what are known as free vectors, which are a set of parallel directed line segments, and the invariant sets of translations are each line parallel to the vector translation. It is because the vector of translation which states that any two vectors of the same length and parallel to each other are considered identical. They need not have the same initial and terminal points. Now, there is only one number of image parts in translation, and it is the image. When we talk of the number of a reflection, if we perform a composition of two reflections over two parallel lines, the result is equivalent to a single transformation of the original object. As you can see in the example, the object is reflected, which means the image will be having a different orientation or facing in another direction. Then, that image is reflected again and facing another direction opposite to it. But if you look at it, didn't that last image face the same direction as the object? And from the object to the last image, it is like disregarding the middle image. The object is translated, thus ending the last image. Therefore, we can now say that there are two reflections in translation. The third geometric transformation we have is called rotation. Now, a rotation preserves orientation. Everything rotates by the same angle in the same direction, so left stays left and right stays right. Therefore, rotations are proper isometries. They are specified by the center and angle of rotation, since rotations have a pivot point called the center of the rotation and they rotate at a certain angle. The invariant set of rotation is their center of rotation and each circle around the center. It is because with rotation, it preserves the distance of points from the origin. Now, there are 2 points or image parts for rotation. It is because we can rotate an object clockwise or counterclockwise direction, and the number of reflection is 2 because if an object like that, the one we are seeing or you are seeing, if it is reflected vertically, it will place down and facing a different direction. And if we then reflect it horizontally, the new image will be placed at the right side and facing a different direction from the previous image. But do you notice that the rotation of the object counterclockwise is reflected in the last image? Thus, rotation has 2 reflections. Now that we have a thorough understanding of isometry and the different geometric transformations, let us now tackle on how we can represent this transformation into matrix representation. But before we proceed, let us first have a brief recap. In mathematics, a rigid transformation, also called Euclidean transformation or Euclidean isometry, is a geometric transformation of a Euclidean space that preserves the Euclidean distance between every pair of points. The Euclidean transformations are the most commonly used transformations, and when it comes to Euclidean transformation, it is either a translation, a rotation, or a reflection. Now, in this part of the lesson, we'll only discuss the translations and rotations only. Thus, we'll be tackling about translations and rotations on the xy plane. We intend to translate a point in the xy plane to a new place by adding a vector hk. To understand it clearly, let us draw a standard x and y to the Cartesian axis, and then we have a point where we call it as our point A that has a coordinate of xy. Now, what we will do is, since we are going to apply translation on these points, we will move this point A with coordinates xy along the vector t. And so, we will end up at this point up there where we will call it point B, which has the coordinates x prime, y prime. Again, we were starting at point A with coordinates x and y. And all we wanted to do is translate point A along vector t where we got this point B with coordinate x prime, y prime. Now, if we define t, the vector t, as vector h and k, then it is not difficult to see that between a point x and y and its new place x prime and y prime, we have x prime equals to x plus h and y prime is equals to y plus k. Simple enough, but we want to do particularly is to translate a whole set of points, not just individual points, and we can do that by making use of a translation matrix. So, we will be using a form similar to the homogeneous coordinates. If you are not familiar with what homogeneous coordinates are, well, homogeneous coordinate system are a system of coordinates used in projective geometry, as Cartesian coordinate systems are used in Euclidean geometry. And in order to convert from homogeneous coordinates x, y, w to Cartesian coordinates, we simply divide x and y by w in x over y and y over w. But this is only if we are dealing with 3D, and this will be touched later. Going back with our example, we are only using x and y. Going back with the point we have, it becomes a column vector whose third component is 1. Thus, point xy becomes the following. From the left side, we were able to come up with this because we know that x prime is equals to x plus h and y prime is equal to y plus k, and our third element is 1. And so we have 1x, so we write 1 there first. Then we have no y at the first element, so we write 0, then we have our h. Next, for our second one, we have 0x in our second component, so we write 0. Then we have 1y, so we write 1, and then we have our k. Then for our final coordinates, we only have 1, so we write 2, 0, and 1, and we multiply it by the element x, y, and 1. Same for our homogeneous matrix on the right side. We know that our first element is equal to x prime minus h. You may ask why minus. It is because we consider its position before it was translated, or if we backtrack along the vector hk. Moving on, we also know that our second element is equal to y prime plus negative k, and our third element is 1 only. So for the first component, we only have 1 x prime. So we write 1 and 0 because here x prime minus h, we don't have a y. Then we have our negative h. Next one, we know that with y minus k, we don't have an x. So we write 0. Then we have 1y, so we write 1 and negative k. For the third component, since we only have 1 element, so we write 2, 0, and 1. Then we multiply that with the component x prime, y prime, and 1. Therefore, if a line has an equation ax plus by plus c is equal to 0, after plugging the formula for x and y, the line has a new equation a prime plus by prime plus the quantity of open parenthesis negative ah minus bk plus c is equals to 0. Now consider what happens when we take a point xy and rotate it by an angle of theta. Using a polar coordinates, we can write xy is equals to r cos alpha, r sin alpha, where r is the distance from x and y to the origin, and alpha is the angle made by the line from the origin xy and the positive x-axis. After rotating xy by an angle of theta, the new point is still r units away from the origin, but now the angle made by the line from the origin x prime, y prime, and the positive x-axis increases by theta. Hence, x prime y prime is equal to r cos alpha plus theta, r sin alpha plus theta, and r sin alpha plus theta. Now let's use the cosine and sine sum of angle formulas to write x prime and y prime in terms of x and y. X prime is equal to r cos alpha plus theta is equal to r cos alpha cos theta minus r sin alpha sin theta is equal to x cos theta minus y sin theta. Y prime is equal to r sin alpha plus theta is equal to r sin alpha cos theta plus r cos alpha sin theta is equal to y cos theta plus x sin theta. Putting this into matrix form gives us x prime, y prime, and our third element 1 equal to the matrix of column 1, row 1, positive cos theta, column 2, row 1, negative sin theta. Third column, row 1 is 0 because in x prime is equal to x cos theta minus y sin theta, there is no third element that exists, that's 0. Okay, next we have column 1, row 2, positive sin theta, column 2, row 2, positive cos theta, and third column, row 2 is 0 because and y prime is equals to y cos theta plus sine theta. There is no third element, is 0. And lastly, we have column 1 and column 2. Row 3 having 0 on both because as you can notice in our third element, there is only one constant, which is 1, and no x and y equivalent. Thus, we put 1 on the third column, row 3. Then, we multiply this to our first element times second element y and our third element 1. Hence, the matrix which rotates a point by an angle of theta counterclockwise is cos theta minus sine theta, cos theta. And if it is rotated an angle alpha clockwise, we will have x is equals to r cos alpha plus theta is equals to r cos alpha cos theta plus r sine alpha sine theta is equals to x prime cos theta plus y prime sine theta. Y is equals to r sine alpha plus theta is equals to negative r sine alpha cos theta plus r cos alpha sine theta is equals to y prime cos theta minus x prime sine theta. Putting this into matrix forms give us xy in our third element 1 equal to the matrix of column 1, row 1, positive cos theta, column 2, row 1, positive sine theta, third column, row 1 is 0 because in x equals x prime cos theta plus y prime sine theta. There is no third element that exists, the 0. Next, we have column 1, row 2, negative sine theta, column 2, row 2, positive cos theta, and third column, row 2 is 0 because and y is equals to y prime cos theta minus sine theta. There is no third element, the 0. And lastly, we have column 1 and column 2, row 3 having 0 on both because, as you can notice in our third element, there is only one constant, which is 1, and no x and y equivalent. Thus, we put 1 on the third column, row 3. So then we multiply this to our first element x prime, second element y prime, and our third element 1. Thus, rotating a line ax plus by plus c is equal to 0. About the origin, a degree brings it to a new question. Quantity of a cos alpha minus b sine theta multiplied to x prime plus quantity of a sine theta plus b cos theta multiplied to y prime plus c is equal to 0. Now, let us apply what we have learned through an example. Find the coordinates of vertices of triangle TRI with point T having a coordinates of 2 and 1, point R having the coordinates of 4 and 3, and point I having the coordinates of negative 3 and negative 2. If it is to be moved 5 units to the left and 2 units up. So we will write first the coordinates of the triangle as a coordinate matrix. So then we will have 2, 4, negative 3, and negative 1, 3, and negative 2. Translating the triangle 5 units to the left means that each x coordinate decreases by 5. Translating the triangle 2 units up means that each y coordinate increases by 2. And the translation matrix that will do this is negative 5, negative 5, negative 5, 2, 2, and 2. To find the coordinates of the vertices of the translated triangle TRI, add the translation matrix to the coordinate matrix. Now, to compute this, we will just follow x minus 5, which is the translation of the triangle 5 units to the left, and y plus 2, which is the translation of our triangle up. Thus, we'll just add 2 plus negative 5, which is equal to negative 3, then 4 plus negative 5 is equal to negative 1, then negative 3 plus 5, we will have negative 8. Then we will do row 2, so 1 plus 2 is equals to 1, 3 plus 2, we will have 5 then, negative 2 plus 2, we will have 0. Based from our results, the coordinates of the vertices of TRI are T, negative 3 and 1, R, negative 1, 5, and I prime, negative 8, 0. And if we illustrate that, it will look like this. To check our solution and answer, let us use the matrix calculator app called MathCalc from STE Math and Dismas Graphing Calculator application to graph our figure and its transformation. And these two applications can be easily downloaded in Google Play. As you can see, we are now checking our matrix result through MATCalc. Upon opening the app, you will already see a blank matrix. By sliding the top and sliders, we can choose what is our matrix, like 3 by 3, 2 by 3, and etc. Okay, for our example, we will be utilizing a 2 by 3 matrix. So, we will just do an adjustment to have a 2 by 3 matrix by adjusting the vertical slider on the left side. We will put our inputs, which are in the column 1, row 1, we will input 2. For column 2, row 1, we will input 4, and column 3, row 1, we will put negative 3 in. Next, we will input negative 1, column 1, row 2. Then we will input 3 in column 2, row 2. And lastly, we will input 2 in column 3, row 2. So what we will be doing is add matrix A and matrix B, right? So in order to do that, we will navigate the middle part where we can scroll left and right to reveal more buttons that would help us choose what operations we will be using. Since we need to do addition operation, we will just simply press the plus button, and the matrix we made will be added to the memory of the app. At the same time, the matrix table is cleared for another matrix to be made to complete our goal. Then we will input negative 5 on column 1, row 1, as well as in column 2, row 1, and column 3, row 1. For our column 1, row 2, we will input 2, and we will also input 2 in column 2, row 2, and column 3, row 3. That would be our matrix B. The next step we will do, since we already have our matrix A and matrix B, is we will press the equal sign from the middle part of the app where the operations are listed. After pressing the equal sign, it will automatically be registered to the application's memory and will be calculated immediately. As you can see, it will register complete information as to the current memory, which is the result of the matrix operation we just did. It will indicate what operations we've done, which is performing addition, then gives the full matrix A plus matrix B that we did and the answer. Additionally, it will give other details like the operations done in order to arrive to our answer. And based from the answer on the app, we got the correct answer. Now, we want to see what that matrix looks like in the XY plane. That's why we will then be using the Dismus graphing application. You are right, Dismus graphing application. Opening our app will be meet with this look. It's a blank XY plane graph, and what we are going to do is input the vertices of our point TRI, and RT prime, R prime, and R prime. And we will also want the points T or I will have a line connecting them to each other to form a triangle. In order to have that, what we are going to do is click the plus button. And we will be given a choices such as f of x expression, the quotation signs for note, a table, and a folder. What we will be using with the table. By clicking that, we will have this table of x and y. In there, we will put our respective vertices. On the x column, we'll input our first vertex 2, and for y is negative 1. Notice that after putting our first vertex, it will automatically be plotted on the xy plane. Moving on, we will now input our second vertices, which is for our x column, we will put 4, and for the y column, we will put 3. Then, we'll put our third vertices to form our triangle. We will input negative 3, and for the y column, we will put 2. Will this be the last we will input? No, because in order for our triangle to connect our last point to the first point, we have to input the first vertex value that we put on the first row of our table after the last point vertex. It is because with Dismus, it won't automatically connect the last point to the first point. That is why we have to input our first point vertex again. So in the first row, we will have 2 for x column row 4 and -1 for y column row 4. Now you may wonder, after plotting this point, how are we going to connect them to each other? Well, for this mess, it is made easy. How? Well, notice in our table, just beside the y column label, there is a circular drawing with 3 dots being connected to each other. We will long press that button. Don't just press or click it because it will only make your points or dots disappear. Long press it instead and be presented with these varieties of options. First, we can choose our points to disappear, leaving only the connected lines. Next is we can change the thickness of our lines. If our points is a solid dot or hollowed one, then we can also choose the colors. And most importantly, we can choose if we want to put or connect them with a line or drag them. But since we want to have our points connected, so we will choose line. Click that option and voila, our points are connected. And we can also change the thickness of our lines, as well as if we want a solid line or a broken line. Now, we will plot our T prime, R prime, and I prime. Same process, we will click our plus button and choose table. Then we will input the vertices of our points. And that I, my math lover, is what our triangle TIR would look like. And when subjected to transform, we will have our triangle T prime, R prime, I prime. We can also observe that they still look the same. And it shows what transformation it have undergone also, which is translation.
Pretty easy so far! As long as you know what transformation is being applied, then transforming a transformation into a matrix representation will be easy. Thank you so much for listening, my dear math hubbers. I hope you have learned anything about our topic on symmetric isometries by hands-on exploration and transformation of the Euclidean plane using matrix representation. See you next time around. Bye-bye!